mailed in regrade partial credit requests, and I haven't had a chance to process those. And that will totally change the scores on these things. So I'll get on that as soon as I can.
I'm sorry, are you taking the questions about the exam right now? Or?
I was just going to talk about one problem. All I said was, if you have questions about specific questions, yes, I can take them now.
Okay.
Go ahead.
Yeah, on number 2, I claim that you don't need any rule at all to handle a non-letter character, that the default action of flex is to just echo the character. There's no rule that matches it.
If you have that in mind, you should say that. So catch me afterwards. So the point is that on problem 2, which was a flex question, people who gave me just rules for the upper and lowercase letters, I said you also need some way to handle the non-letter characters, and I think I took off what, half a point? Yeah. And people who actually said you don't need to do that because they'll get echoed to standard out, didn't get that half point taken off. The problem that people had most trouble with was the implementation of finite automata. So let me quickly show you where that stuff came from. So where that came from was here. This thing is slow. So that's where this came from. Okay, how do you implement finite automata? That you can implement them using code, and that's what the code looks like. Or you can implement them as tables, table-driven automata. So that's where this came from. Now, what I did notice in the answers, though, is that there's some confusion about all the various automata we've been talking about. And we have talked about a bunch of automata, so let me very quickly go over the alternatives there. When you look at various kinds of automata, for example, if you're in an automata theory class, there are automata of the wazoo. So let's quickly summarize the briefly the ones that we've looked at. There are finite state automata. So we studied these. These correspond to regular languages. And the automata, implementations that I just showed you correspond to these. Okay, so this is what is used in lexical analysis for recognizing tokens. So my recollection is that on that problem, I think it said lexical analysis on the heading. No, just at finite state machines. But there's this parenthetical remark, the code generated by Flex uses one of them. So that's a giveaway that we're talking about lexical analysis. So these guys, you just have a bunch of states and you're bouncing around between the states. Okay? There is an extension of this called Pushdown Automata. which correspond to context-free languages. And these guys look like finite automata. They look like these guys plus a stack. Okay, so think of these as FSA plus stack. Now, in terms of an implementation, these guys need very little machinery, right? All you have is a finite set of states, and you bounce around between the states. These guys need a bit more machinery. So there's the finite state, the finite control that's over here, that we had over here, plus the stack. And because you have a stack to deal with, the implementation techniques are somewhat more involved than this. The ones that we studied actually keep the state on the stack. They push the states on the stack, right? You don't need to push the states on a stack over here because you don't have a stack to deal with, right? You just have a fixed finite set of states for a given automaton. As long as we're talking about these guys, let me say another thing, because the next thing that we'll be talking about is going to be semantic analysis. Okay, so type checking and stuff, checking declarations. Suppose I have an input of size n. Okay? How much time, asymptotically, big O complexity, how much time would a finite state machine take to recognize, to decide whether that input is in the language it's accepted by the finite state machine or not? Sorry?
And, I mean, the worst case is it has to read every character.
It has to look.
Character it either accepts or rejects.
That's right. So this is big O n, right? Because each character is looked at once, and we just chug along. And for each character, you do a fixed amount of work to keep track of the states.
The flex documentation, I think it says that for every character is compared at most one time.
That's right.
At most one comparison per character.
That's exactly right. So you have linear amount of time. It turns out that context-free languages, as you would expect, are more complicated. They take more effort to recognize. So there's a fair amount of literature in the context-free language world, because sometimes context-free languages can be ambiguous, and while we don't deal with them, people have looked at parsing techniques for ambiguous context-free grammars. And long story short, for an arbitrary context-free grammar, you can still decide whether or not a given string is in the language of a grammar in time order n cubed. Okay, this is arbitrary grammars. For the languages that we've been looking at, for the parsing techniques, okay, so we've been talking about LR parsing, which doesn't include all possible context-free languages, right? Because there are, if a language is ambiguous, it's going to have conflicts when we go to generate a shift-reduce, a parsing table for a shift-reduce parser. And if it has conflicts, then that grammar is not parsable. So let's suppose that I have a grammar for which I don't have conflicts when I go to generate a parse table. How much time does that take? Same reasoning as in the previous case. You look at each character exactly once, each input character. And for a given character, I do a fixed amount of work, right? I take the input character, I look up the parse table, I do a fixed amount of work. So it turns out that for LR parsers, it's order n. That's not too bad. So I'll go and in just a little bit of time we'll revisit that, because we'll start looking at the problems involved in type checking and some of the sort of theoretical background for that. Okay? So before I go on, for the midterms, the one problem that a lot of people had issues with was that one about implementing finite state automata. And I just wanted to touch on that. Another one that quite a few people had issues with was the last one, not the last one, the penultimate one of the, well, whichever one it was, the one you had to compute closures and go-tos. So I was surprised at that. At least one person said, "What is this? You're asking about first sets and no follow sets." This person was really quite disappointed. And so was I. It turns out that the copy machine ate the follow set question. I think that was the week we were having all these storms. And when it's humid, the paper sticks. And it fed two sheets together. And so the sheet with the follow set problem didn't get printed, which is why there was no part B to question 5. My carelessness, I should have checked it sooner, mea culpa, etc. So anyway, that's why you didn't have, that's why you guys didn't have a follow set question. Now, John, you have a question?
Yeah, going back to the previous one you were talking about,
Mm-hmm.
that was for the finite state machines.
Mm-hmm.
Is that the answer then? The finite state automata versus Pushdown automata?
No, the answer that I was looking for was that you can do it using these two techniques.
Okay, so what you did on the board there is unrelated.
What I did on the board is related, but it wasn't what I was asking about.
Okay.
Yeah, so these are the things that I was looking at. How are they implemented? Implementation technique 1, implementation technique 2. Okay? All right. So I didn't have any other intention of covering the final exam, not the final exam, the midterm exam right now. But if you have questions about the grading of your exam, please do talk to me, okay? So let's see. We've talked about bottom-up parsing. We talked about SLR1 parse table construction. So this is what we actually did an example about last week, right? Last Monday. You take the grammar, you augment that with this S prime, new start symbol S prime, add a new production, S prime goes to S. Then you compute the sets of items, right? So what you're looking for is the deterministic version of this guy, deterministic pushdown automaton. That's what we're trying to construct. That's where the sets of, so you begin with the initial state, which is S prime goes to dot S, compute the closure, and then you compute all the possible transitions that you could have using closure and goto, okay? That gives you a set of states in the parse. So each state is a set of LR0 items, okay? Those are the states of the pushdown automata, and from that we construct the parse table entries. So the way you do that is, for SLR1, I look at each state. Each state is a set of items. So now, if a state has an item that looks like there's a terminal to the right of the dot, then I have a shift action on that terminal in that state. Okay? The intuition is that in this state, if I see this token in the input, I can legally continue parsing. If I have an item where the dot is all the way at the end, I have a reduce action for that production. I'm sorry, for that state using this production for everything that's in the follow of that corresponding non-terminal. Okay, so I just examine the different items in each state, and as I go down, I sprinkle shift and reduce actions into my table. It's entirely possible that a table might get a shift action from one item, an entry in the table might get a shift action from one item and a reduce from a different item. And if that happens, I have a conflict. Okay, So if a state has multiple entries, the grammar is not SLR1. So we actually had gone and looked at an example, and that worked out nicely. So SLR1 is nice and simple, and that's the reason we talk about it in the class. But it turns out that there are, in fact, many reasonable grammars for which SLR1 is not good enough. Okay? And by not good enough, I mean that when I construct the parse table, there will be conflicts in the table. Part of the reason for this is that SLR1 is much too generous with reduce actions. It goes and throws in a reduce action for everything that's in the follow of each non-terminal. Okay, and that can be too much. And here's a simple grammar. We could work through the example for this, but this is a simple enough one that, you know, I would suggest going off and doing it on your own. You'll find that there is a state where I have a shift action from equals over here, but there's also this item, and I throw in a reduce action for follow of R. I'm sorry. What's in the follow of R? Everything that's in the follow of L is in the follow of R. And equals is in the follow of L. So that gives us equals in the follow of R. Okay? So this gives us a shift-reduce conflict. So what do we do to cope with things like this? Essentially, what this comes down to is that the approach that we've taken so far of having a reduce action for every token in the follow set gives us too many reduce actions. Okay? So one can think about it in a couple of ways. One way is that I can take a state. So if you think of this as a state in my parser, and I have, you know, some item and another item. So I have a whole bunch of different items. And some of these items generate shift actions, other items generate reduce actions. And that can cause conflicts if in the same state, one item generates a shift action and a different item generates a reduce action.
For a given token.
For the same token, that's correct, right? So if you, in the parse table for the same cell, state token pair, that's exactly right. So one way I could potentially reduce the number of such conflicts and hopefully eliminate them is to think of breaking this state up into pieces. And if I do this carefully, and the grammar is good, it's kind of suits us, then maybe now the shift action's over here and the reduce action's over here, and now I don't have a conflict. So splitting up the state might help eliminate some situations where I get shift-reduce conflicts. It will give me more states, however, because each state now gets split up into more. So that's the intuition, that we can enhance the LR parsing algorithm by somehow splitting up states into more states. Each state gets split into more states. So the parser has a lot more states, but hopefully there are fewer conflicts. So what happens is that, and the way we do this is by incorporating something called look-ahead tokens into the items themselves. Okay? So previously, when we were discussing SLR1 parsing, we had what we called LR0 items, right? We had LR0 items. So these things, an LR0 item was just a production with a dot somewhere on the right. So now we'll have, and the LR0 item meant that the item had 0 look-ahead. The only look-ahead was in the parser, but the items themselves didn't incorporate any sort of look-ahead. So what we'll now do is add a token to each item. So now the items themselves have a little bit of look-ahead in them. And I'm not going to go into the details of that because we could chase this till the cows come home. I'm just going to mention that the way you deal with some of the weaknesses, this main weakness of SLR1 parsing, is that each item now has an additional component, which is a lookahead token. So these are now called LR1 items, because the items have one token lookahead. Okay? We're now beginning to throw about zeros and ones all over the place generously, and this gets awfully confusing. So let me distinguish what's happening when. The items, which now have one token lookahead incorporated into them, and I'm just giving you this as a 20,000-foot view, really, really high-level view. I'm not going to go to the details. We don't have the time for that. I'm going to talk about type checking for most of this lecture. The items that have one token lookahead, that is processing that is done when the compiler is being constructed. Okay? That is well ahead of the actual parsing process. When the compiler is being constructed, the items have some additional information, some additional bookkeeping that they do. We call that one token lookahead. That is completely different from the parser's one token lookahead, which happens when the compiler is executing. When you type GCC and it starts parsing, that uses the next token to determine what it should be doing. And that is one token lookahead at parse time. So there's one token lookahead in the items at compiler construction time when GCC is being built, like when you type make and GCC builds or your compiler builds. That's when the LR1 items lookahead comes into play. There's the parsing lookahead, also one token, but that's the compiler or the parser using the next lookahead token, the next input token, to determine what parsing action it should take. The two are very different. The nomenclature is very, very similar and potentially confusing. Okay, so keep the two in mind. The items are at compiler construction time, when the compiler is being built. The other lookahead is when the compiler is running. Okay? So it turns out that when I incorporate my one token lookahead into the items and I split up my states, that does work, and it's very successful in eliminating a lot of the conflicts that arise in SLR1 parsing. So what you get is called an LR1 parser, and that is much more powerful. It's able to handle everything that an SLR1 parser can handle, and it's able to handle grammars that SLR1 cannot handle. So this is great. This is the good news. In computer science, there's always a but. There's never a free lunch. And the but is that there are so many states, because each state has now got to split up into a whole bunch of them. There are so many states that your parse table gets really big. Okay? Your parse table gets really big, and that can be a concern. Okay? Perhaps less so if you have 8 gig of memory, but it can be a concern. People don't like that. One reason is that even if I have 8 gig of main memory is really slow. Okay? And these parse tables don't really have any effective notion of locality. So when your parser is sitting in a loop accessing the parse table, right? So your, say, action is parse table sub, action table sub, current state, and next token. You're stomping all over that table. And that does not do well with cache memories. Okay, so performance suffers even if you have a boatload of main memory, because ideally you'd like to process a small amount of data that's sitting at the top level cache, level 1 cache, and you just like to hum along on that. And when these parse tables get big, that doesn't work very well. So people noticed that, in fact, some of the states in an LR1 parser look really, really similar, and they act really, really similar. And people said, you know what? Just the same as ducks quacking and walking and so on, these tables really should be the same. So people said, well, suppose we merge these tables. We just make them the same in the parser. that means I have fewer tables to contend with, right? I mean, fewer states to contend with because I've merged certain states. Did I say tables? I'm not awake yet. I have states that look really, okay, scratch what I said previously. Here's what I mean to say. I have different states in my LR1 parser that look really similar and that act really similar, whose actions are very, very similar. So the question is, what is gained by having distinct states that look so similar? Let's just make them the same state. And let's just do that throughout the parser. Well, if you do that, and if you do it carefully, it turns out that you sort of kind of have your cake and eat it too. It turns out that if you do it carefully, you don't go back to everything being blobbed together into a single state. Okay? A whole bunch of states get merged, but not all of them. Of course, there's a but. And the but is that in the process of merging states, there are some situations where states that didn't have conflicts previously could get conflicts now. So the process of merging states can lead to a loss of power, loss of expressive power. Question?
Did you say it's merging almost identical states from the compiler construction time with those of the parsing time?
This is all happening at compiler construction time. Okay. What happened is with LR1 parsing, which is when we introduced look-ahead into the items, in order to split up the SLR1 states and reduce the amount of conflicts, this was very effective and it gave us a lot of states. As a result, the parse tables were really, really big. So what we're saying is, let's look at the parse table and reduce the size of the parse table by merging states that look very similar. So all of this is still happening at parser construction time, sort of like your assignment 2 construction time, okay? So if we do it carefully, you can merge a lot of states, but still not go all the way back to the SLR1 situation. So now you're sort of somewhere in between. You have more states than the SLR1, but a lot fewer than the LR1 case. That's called LALR1. Okay? So the LALR1 takes this idea of the lookahead token in the items, but it merges some states to make the parse table smaller, and the result is a decent compromise, and it improves parsing power. So that's all I will say about LALR1. Okay, we'll pretty much stop there. Error handling, this is really, really, really quickie. You guys have actually all done error handling, and most of you have done a pretty decent job. So you know how to do error handling. But I think it's worth going over this very, very quickly, because I remember the very first C compiler that I dealt with. This was on a VAX that belonged to what's now called UITS. At the time, it was called CCIT. And I wrote by C compiler. The compiler was actually the interpreter for a Prolog system. This is a long time ago. So I tried to compile it, and it chugged along for a while. This is on an old VAX. And then it said, syntax error. Oh, OK, now what? So that's unacceptable. In fact, I can imagine a compiler might choose to ignore the error, and that is unacceptable. I mean, that's just, there's no excuse for that. Okay? If there's an error, you need to tell the programmer what happened. Okay? You can crash or quit on the first error. That's not good either. But I have seen compilers that do that. But you know yours doesn't. So you're already better than some real, quote-unquote real compilers that people have produced in the past. So you should continue to process the input, okay? But once you find an error, it makes no sense to do code generation, okay? If you think of the process of compilation, in fact, the process of program development, the most expensive resource is programmer time. Okay, by far the most expensive resource. And in any endeavor, what you want to do is you want to optimize the usage of the most expensive resource. What that says is that what your compiler should do is process as much of the program and find as many errors as it can. Okay, find as many errors as it can, so that you don't have the programmer having, finds one error, fixes that, submit, does another compile, find another error 2 lines down, and iterate over this. That's painful. So you want the compiler to go on, find as many errors as it can, report them in a sensible way, so the programmer fixes them. And here we're trying to optimize the amount of time the programmer puts in. There's a whole separate, along the same line of optimizing the programmer's time. There's a lot of work that people have done on making the compile process as fast as possible, so that the time interval between when you type make and the whole thing builds can be minimized. The compiler itself is blazingly fast. And there's all sorts of issues that come up when you're trying to deal with really, really large programs, like millions of lines of code as you would in an industrial setting, right? And you're trying to process this really, really quickly. So people worry about things that you wouldn't think about. People who pay attention to making really fast compilers, for example, worry about how long it takes to do includes, hash includes. How long does it take to suck in an include file, process its includes, process them recursively, and so on. So to go through a lot of effort to not do that kind of recursive includes and stuff. But that's a topic that we won't get into. So the compiler needs to recover as best it can and continue to process the input. This will be true. This was true of syntax errors. This will be true of type errors and other semantic errors as well. Okay. Of course, it doesn't make sense to do code generation now. So you turn off code generation. You guys have seen this already. Once you see a syntax error, once something has gone wrong, it's not always easy to recover. And it's not clear sometimes what recover means. Right? So sometimes what will happen is that if you see an error and you're trying to recover, and maybe there's another error very soon thereafter, you might miss that. So these things happen, right? There's no way for a compiler to be perfect. There's no way for the compiler to intuit what the program was trying to say. People have tried. In the 70s, there was a little cottage industry for a while of people saying, I think I know what you meant. And they would try to repair the error. And the way they did that, well, essentially they would try to take an erroneous program into a similar but legal input. Now, what was the paper clip in Microsoft Word? The thing that's really annoying. It tries to tell you what you should be doing. And most people that I know just turn it off the first time it comes up. So this was sort of kind of like that. It tries to tell you what you should. This is what you meant. You said, that's not what I meant. But it was entertaining to think of how they go about doing that. So I'll mention that to you. Have you guys heard of a phrase, Hamming distance? Hamming distance, anyone else? Where Hamming distance comes up is in error correcting codes. Okay, so you have a bit sequence. And the way you construct these codes is you throw in a few additional bits, okay, so that if there is, for example, you have a 1-bit error, you can show that the actual bit that's transmitted. You can use Hamming distances to figure out what must have been sent in, what the actual sequence must have been, so you can correct 1 bit of errors. I think you need 2 or 3 additional bits for each in order to correct 1-bit errors. This is used in error correcting codes all the time for data transmission. Okay, so you transmit a little additional data, and you use the notion of Hamming distance to find the closest bit pattern to the erroneous one. Okay, and if there was just 1 bit that got thrown off, then the closest one is in fact the right one. Okay, so with what I think I think with 3 additional bits per byte that is sent, you can detect 2-bit errors and you can correct 1 bit. I've forgotten the details. It's been a long time. But the notion of Hamming distance is what is the nearest correct bit pattern to the thing that you're seeing, to the erroneous sequence. So these guys, they used an analogous notion of Hamming distance. It's not exactly the same thing, but essentially conceptually analogous thing to say, what is the closest, what is the nearest correct input to the one I'm seeing? That must have been what it was. And of course, you know that's not going to work. Anyway, so quick summary. You guys have done error detection, error recovery. You guys have been giving good, informative error messages. Good job, everyone. If you haven't, then consider yourself castigated. And you will continue to do a good job on the semantic errors. You'll give me good, informative type error messages. And no code generation, right? OK, Steve.
In reference to attempting to repair the errors stuff, I can't think of any specific examples right now, but I feel like doesn't GCC with its warnings and stuff like that kind of do something similar because it's not, exactly what's supposed to happen? I don't know. Like I said, I can't think of any.
Yeah. So actually, I take that back. I misspoke. When I was describing Hamming distance stuff, I was talking about error correction. So repair is slightly different. With GCC warnings, what GCC is doing is it's looking at common types of errors or mistakes that aren't, strictly speaking, errors. If it's a warning, that means that the input is syntactically correct. Okay, so therefore, it's just a warning. It's saying, hey, you might want to come back and look at this. And that's why you can suppress warnings if you want. You can turn on warnings. You can say -w all, and it'll give you a bunch of warnings or not, right? And if you don't say -w all, then some warnings won't appear. So with warnings turned on, for example, it'll actually look at the arguments of printf and say whether you have too many arguments, too few arguments, and so on, right? But that actually makes the assumption, which is most commonly true, that printf is calling the C library function printf. But I can define my own printf function, and that'll work just fine, in which case that error is kind of bogus, right? So warnings are just heuristics, kind of common patterns of mistakes, but they aren't really, really wrong. But when we're talking about errors here, this is where the grammar says one thing, the programmer says something different, and the two don't match up. What I was talking about earlier about Hamming distance and all actually apply to error correction. The sort of thing that I meant by that I should have said about repairing is where, let's say you're processing the input, and so you've seen the keyword while. Now the next thing that you expect is a left paren, right? That's what the syntax is. When you see a while, left paren expression. And suppose the token that you see is something in the first of expression. Okay, so now what an error repairing compiler could do is to tell the programmer, hey, there's a syntax error here. But it could pretend that it saw a left paren and keep going. Okay, and that recovery action is slightly different from saying, oh my God, there was a while and now I see X, and yikes, I'm broken. Okay, so it can take it takes a little bit more machinery to say, at this point, if I see one of these tokens, I'll pretend that I saw left paren. I must give an error. I must signal an error, but I'll pretend that I saw left paren because what I'm seeing is, this is in the first of expression. So maybe there was a left paren there, and keep going. And you can think of other such for common kinds of errors. The common ones, omitted left paren, omitted left brace, and so on. Those are useful primarily for compilers for use by novice programmers. Right? So if I'm writing a compiler for, let's say, CS127, then I may not put a lot of effort into code generation because most of those programs won't get executed all that often anyway. But maybe I'll put a lot of effort into the error recovery and error messages, because these are going to be used by novice programmers. Whereas if I'm writing a program for use by, let's say professionals writing high-performance scientific code, the error messages might be minimal, or they'd be de-emphasized.